Hello, everybody. Welcome to the webinar of the Task 46 within the Technological Collaboration Program of the International Energy Agency. It's a webinar about the life cycle assessment of electric vehicle. I want to welcome you all wherever in the world you are currently watching our webinar. My name is Gerfried Jungmeier. I'm working as the principal scientist at Joanneum Research in Graz, Austria. And my expertise is on life cycle assessment, and that's why I have the pleasure to lead the Task 46, dealing with the life cycle assessment of electric vehicle since 4 years already. Before we start our webinar in detail, I want to talk and bring to you the housekeeping rules. All of you are muted, so all the attendees are muted, but you will have, after the two presentations, the possibility to pose questions in the chat. And when you do so, please introduce yourself also in the chat window, that we know your name and also the country and the institution where you're coming from. By entering this webinar, you have already agreed that this event is recorded and it will be made available afterwards. The agenda for today is I will give a very brief introduction, mainly on the activities of Task 46 and the Technology Collaboration Program on electric vehicles from the International Energy Agency in general. Then I will give a presentation on the climate neutrality and circularity assessment of electric vehicles. I will use an example of trucks and assessing the climate neutrality and the circularity. The second presentation will be done by Robin Smith from the Transport Energy Emission Research from Australia, and he will focus on specialities of battery electric vehicles and life cycle assessment. And then you have the possibility to ask questions in the chat, and we two speakers will answer these questions. And for all of those who missed the first webinar we had in November already, the first webinar was on the basics of life cycle assessment and its application to electric vehicle, and it is also available online. So if you're interested, you can also watch later on the first part of this webinar. So what is the Electric Vehicle Technology Collaboration Program? It's an international membership group collaborating under the International Energy Agency framework. It was formed in 1993 to produce and disseminate information about electric-driven vehicles, mainly battery electric vehicles, hybrid electric vehicles, and fuel cell electric vehicles. And the idea is really that the different countries participating and then members discuss about their respective needs, share key information, and learn at least from the pool of electric vehicle experience all across the globe. Currently, we have 18 countries participating in this technology collaboration program. And here you see the impressive list of the different participating countries. Additionally, it's also the European Union is joining this, this collaboration program beside the different countries you see here on the screen. Coming back to the objectives and activities of this IAA task, which is called Life Cycle Assessment of Electric Trucks, of electric buses, and any other electric vehicles. And we also put a focus on so-called vehicle-to-X services like vehicle-to-grid, vehicle-to-home frequency services within the assessment of environmental effects using life cycle assessment. Of course, if you only look on electric, battery electric systems, it's not enough. You always have to compare it to other systems. And in our case, we compare it on one hand to fossil fuels, the conventional fossil fuels, but we also compare it to vehicles using renewable hydrogen made from renewable electricity. And we also compare it to e-fuels made from CO2 and also from renewable electricity. And this is at least the main challenge and the systems we are considering. And all our view on this different system is always based on life cycle assessment, where you have on one hand the transportation service we all need for our mobility needs, and on the other hand of the system boundary, all our life cycle assessment always starts in nature by taking raw materials or energy from nature, which is then technically transformed via different process steps to the transportation service. So far, we are really a long, impressive list of 12 participants from the different country. I will not mention them all in detail, but at least we have 12 participating countries. We have also established a collaboration with another technology collaboration program on alternative motor fuels, because in the area of e-fuel, that was a very good synergy using also expertise from another collaboration program. And then we have 2 observers, so in total we are 14 participants contributing to this activity. In general, again, coming back to the technology collaboration program, in total, we are running currently several different tasks in many different areas. It's about electric freight vehicles, about technology in that area. It's about marine application, electricity use in harbors and in ships, but it's also dealing with critical raw materials or with raw materials in generally you need for the electrification of different transportation modes. And also we are dealing with use phase, with battery swapping, with economically modeling and systems that are really able to make also the electric systems economically useful. And this webinar is at least centered around one of the ongoing research tasks. It's the task 46 about the LCA of electric vehicle. And we're going to take you through some of the research and the findings so far. And I will start now with the first presentation, which is at least at the work we did in task 46 in the last 1.5 years, where we worked on the climate neutrality and the circularity assessment of electric vehicles. I will show you the methodology and how we applied this methodology also in a case study on trucks. I will start on the very beginning with the conclusions from this case study, that you already get an impression what will be the main results and outcome we found in this LCA case study. We found out that climate neutrality potential and the circularity potential are additional and environmental categories in a so-called dynamic life cycle assessment, which are not yet covered in the conventional impact assessment categories you normally find in life cycle assessment. We've also seen that only systems that use renewable energy have the principal potential towards becoming climate neutral and towards circularity. So renewable energy is a key to reach climate neutrality and circularity. We calculated the circularity potential, and we found out that the electric systems use direct electricity via batteries or renewable hydrogen or even e-fuels have a relative high, have a similar high circularity potential, whereas a diesel truck has a very low circularity potential due to the use of fossil diesel, because in circularity aspect, the using of diesel, of course, is not circular. You just burn it and the greenhouse gas emissions end up in the atmosphere. In general, maybe not very astonishing that in these categories we have analyzed the truck. The diesel truck has the highest environmental impacts, and On the other hand, we have seen that the battery electric truck really using renewable electricity has the best environmental performances, at least these categories we have analyzed. It has the lowest primary energy demand. It has the lowest greenhouse gas emission. It has the highest climate neutrality potential. It's not climate neutral, but the potential is quite high. And it has the highest circularity potential. So these are the key findings from our analysis. But if you are interested now how we come to these conclusions, of course, I encourage you to further follow the presentation. At least we started on the very beginning saying that global warming, climate neutrality, and circularity are the key challenges we are currently facing. And at least it's the application of life cycle assessment that is the only methodology that is really able to cover and judge and assess these different environmental effects. So life cycle assessment is a principal tool now established to judge on environmental effects. As far as you come to climate neutrality and circularity, you have to apply a so-called dynamic life cycle assessment, which is a specific further development of life cycle assessment, because there it's very important to consider also the timing of the greenhouse gas emission, the timing when you start to extract or when you start using raw materials, and of course when your reuse or recycling started in the overall life phase and lifetime of the considered vehicles. So I give you an example how this look like. So if you look on a vehicle, you have in the life cycle the production phase, the use phase, and the end of life phase, and the time is running on the x-axis, whereas different environmental effects like greenhouse gases or materials are on the y-axis. And here you see two different systems. You see they have a different accumulated emission in the production phase, in the use phase, and the end of life phase. But of course, in LCA, if both systems provide the same service, on the very end, after the lifetime of the vehicle ended, you see if B is lower than A, you can clearly say that the vehicle B has lower environmental impacts. And there could also be a system C looking like this, maybe a higher emission on the very beginning, but during the operation phase, this line flattens, so you can still provide transportation service while not adding very much additional environmental burdens to the overall service. And in the end of life phase, of course, maybe we can also decrease the environmental effects. Yeah? And this is at least the system we are most interested. One example is if you have an electric vehicle, if you buy it today and plug it in the Austrian electricity mix, you roughly get 75% renewable energy. But during the lifetime of this electric vehicle, the electricity generation system in Austria will change, because we have a national goal that in 2030 only renewable electricity will be available in our electricity grid. And that means as you get a different electricity during the lifetime of operating the electric vehicle, you at least have a development where you say you still can provide transportation service, but no additional greenhouse gas emissions. And this we call towards climate neutrality, this flattening of the curve. And the second important thing of this system C is this decreasing effect in the end of life phase. This means if you're really able to recover some or even more, or even most of the material you put in the system, if you can recover this material and reuse it for any other further product, of course, this is also going in the right direction because it's towards circularity. So this is at least the system we are most interested in, to find systems that go towards climate neutrality and towards circularity. Finally, everybody's talking about climate neutral transportation system. And so far in our discussion, we say a climate neutral system is only possible if you combine it with a carbon capture and storage system using renewable electricity to capture CO2 from the atmosphere At the same time, for example, here in the graph, at the same time, the green system is emitting greenhouse gases. If at the same time, the carbon capture and storage absorbs this carbon or CO2 and stores it forever underground, this might be a principal system that is really climate neutral because you have no greenhouse gases in the overall lifetime. So when we talk about climate neutrality and circularity, of course, the most important thing is on the very beginning to define what is climate neutrality and what is circularity. And this definition you see here is really dedicated to be applied within life cycle assessment. And we say a system is climate neutral and circular if in the whole life cycle covering production, operation, and end of life phase, if you only use reuse components or secondary recycled material, and you only use renewable energy. And while doing so, you also make no waste and no greenhouse gases. Yeah, so if you fulfill these requirements, no primary energy, no waste, and no fossil energy, at least then you say this is really the ideal climate and circular transportation system, or which is valid, at least I think also for other products and services. And using this definition, we have developed two indicators. We have an indicator measuring the circularity potential, which the material circularity index is between 0 and 100, or between 0 and 1, where 0 means a linear system, where you put everything is becoming waste, where in a circular system, everything is really in a closed cycle. Secondly, we have an indicator for the climate neutrality potential, because based on the greenhouse gas emissions over the lifetime of the vehicle, we're able to cover the total radiative forcing at the top of the atmosphere based on these greenhouse gas emissions. It's counted in watt per year and square meter. And if this is really 0, then of course you're fully climate neutral. As you've seen before, the most realistic case would be in the years to come that we have systems that go towards climate neutrality, which means at least no additional greenhouse gas emissions in the operation phase. The conclusion from this definition is that you really see that climate neutrality and circularity are really visionary and very long-term targets. You don't reach them today, and I think maybe not tomorrow, but it's at least the right direction. And we really have to see if our products and services we are now developing, that at least they show that they have the potential to become climate neutral and circular, and at least that they go in the right direction, which means towards climate neutrality and towards circularity. Why is it so important? When you have the greenhouse gas emissions, you see here in the graph saying that the greenhouse gas emission is something different than the climate neutrality potential. You see here on the left-hand side, 3 systems. They have on the very end the same, they provide the same service, and on the very end they have the same, for example, greenhouse gas emissions. But you see the systems, one system has the highest emission in the production phase and a very low emission during the operation phase. The red system is having the highest emission during the operation phase, and the black system is having the highest emission in the end of life phase. So in a normal LCA, you would say all the systems have at least the same service and the greenhouse gas emissions, so there is no difference. Therefore, it's so important on one hand to really have the timing of these emissions over the lifetime on one hand, and secondly, to really count the radiative forcing potential at the end of life of the overall system, because there you see how much these greenhouse gas emissions are heating up the planet. We all know that if you emit greenhouse gases today, of course, a part of these emissions is decreasing and disappearing mainly in the ocean over time. And the later you emit, of course, the later this process starts. So this climate neutrality potential is a way to really measure also and judge on the timing of the greenhouse gas emissions. And here you see on the end of life that the black system is having double radiative forcing potential, for example, than the blue one, depending on really when these emissions occur. And this is one of the key aspects to say we really have to assess climate neutrality based on greenhouse gas emission and its timing. And the second important thing is this circularity potential, where we used as a starting point the material circularity index, which was developed by the Ellen MacArthur Foundation, which including on one hand a material factor and on the other hand a utilization factor. And you can calculate this factor. The more you use renewable energy, the more you recycle, and the more you reuse materials, of course, the higher this circularity factor is. We did a small application looking on the battery EU regulation, where they have binding targets of using recycled material and certain recycling efficiencies and collection rates. And you see here the current material circularity of a battery today of 2030 and 2035. If this rule from the EU battery regulation are applied, you see that the circularity is really increasing from roughly 40% over more than 60% in future. And so in our case study, we analyzed many different trucks. We looked on small trucks, on medium trucks, and the big trucks. Today, I will only focus on the small trucks, but if you're more interested, of course, you can ask me. We have published this paper already at a conference, so the whole work is already available. And most interesting or most relevant in this, beside the different trucks, in this analysis, we use only renewable electricity, because only with renewable electricity, all these systems are really gaining the highest environmental benefits. And additionally, we also say we need to build new electricity generation plants. Yeah, so also the building of the new electricity generation plant is part of this LCA. So we're not only building the truck, we also have to build at the same time the facilities for additional renewable electricity, but also in comparison the facilities you need for hydrogen production and also for e-fuel production. And additionally, we have also a big question on our LCA case study. There are so many environmental impact categories on a global, local, and regional level you find in conventional LCAs, but none of them is really covering the climate neutrality potential and the circularity potential. So for us, it's very important to see if these are really new impact categories not covered by any of the already existing categories. Here you see a final result, as most of you maybe have seen already before. You see the greenhouse gases and the primary energy demand for the different systems we have compared: the diesel, the e-diesel, the electricity, and the hydrogen. And you need as a minimum the primary energy and the greenhouse gas emissions, because you see the results on an energy side are quite different from the greenhouse gas emission side. So this is at least a conventional result. We are all used to it, but here you do not see or are not able to calculate the climate neutrality potential. Nevertheless, you still see which of these systems has the lowest greenhouse gas emission and which of the system has the highest energy efficiency. So in our assessment in this dynamic LCA, we get at least the same results. Yeah, you've seen before, but you see how the emissions are accumulating over the lifetime. And you see here, for example, that the system using renewable electricity, like hydrogen, e-diesel, and electricity, they have more or less a flat line during the operation phase because they use renewable electricity, and this guides you towards climate neutrality. On the other hand, you see that the diesel system has a steady increase in greenhouse gas emission due to the use of diesel. But very important also to see that in the construction phase, on the very beginning of these systems have in the construction phase, when you build the truck and especially all the infrastructure and the electricity generation, in the beginning, they have a significant higher greenhouse gas emission than the diesel system. But over time, these systems are really have the potential to become climate neutral, to go in the right direction, which you can also see on the climate neutrality potential on the right-hand side, that these systems, at least you can compare the radiative forcing potential. The decrease in the end-of-life phase is mainly due to the longer lifetime of the electricity generation system, which lasts at least for 20-25 hours, where the truck is only lasting for 10 or 12 years. So on the very end, the electricity system and the infrastructure can be reused for any other purpose. That's why in the LCA you have to allocate these positive effects in the considered system, and that's why in the end-of-life phase, these effects are decreasing and give you the final value on the end of life. The same further picture, if you can do the same picture if you look on the primary energy in total, the primary energy in total on the left-hand side. More interesting is the share between renewable energy and fossil energy. And you see here that, of course, most of you know that the e-diesel system, you need so much more electricity to drive a kilometer compared to hydrogen, and you even need significantly less energy when you drive with electricity. So using the renewable electricity for a truck service is much more efficient. You need much less energy for the same ton kilometer in our consideration compared to hydrogen and compared to e-diesel. And last but not least, I'll show you some results of our circularity potential, where we looked on one hand first on the different components. We're starting, for example, with the trucks. So if you look only on the trucks, on the left-hand side, you see that the truck is having a higher circularity potential, for example, than the battery electric truck or the hydrogen truck. This is because of the fuel cell and the hydrogen tank, because due to the battery, which have a lower circularity than, for example, the diesel engine and the diesel tank. On the other hand, you see on the right-hand side, you see the same analysis for the electricity supply, but also for the supply and production of hydrogen, of e-fuel and diesel, where they also have a different circularity potential. In the overall system, if you combine now, based on the mass balance over time, the circularity of all the components you need in the life cycle to provide a transportation service, you see finally that the diesel is having the lowest circularity potential due to the use of fossil diesel. So much of the mass being used as diesel, which is not circular. That is the reason why the diesel has such a low circularity, where the other systems using renewable electricity have a similar circularity in the range of a 60%. The circularity can also be shown over time, because the circularity potential in the very beginning always starts in nature. In nature, everything is circular. So you start with 100%, and when building the system, of course, you're decreasing the circularity. And in the operation phase, you see that the diesel is further decreasing circularity, whereas the other systems, mainly using renewable electricity, have a relatively constant circularity. And on the very end, due to the reuse of mainly the electricity system, but also the charging system and the hydrogen production system and so on, you get an increase on the end of life phase, because you are able to reuse main parts of the system for any other system after 2037. So this means also this system is going towards circularity, but with the 60%, it's still far away of being really 100% circular. The overall result just summarize what you have seen so far, and this also shows you that the electricity battery electric system in all of the components has the best environmental performance, and the diesel has the worst performance, except this primary energy total demand, which is higher for the e-diesel and the hydrogen. And yes, we can answer the question on the very end. We think that climate neutrality potential and circularity potential are really two additional impact categories not yet covered in life cycle assessment. And That's what we wish us for the future, that we really all apply a dynamic life cycle assessment by really timing greenhouse gas emissions, material extraction, material reuse over time, that we're really able to judge on the overall system and to identify which systems in the very end have the highest environmental benefits. I would not repeat my conclusions again. I've done that on the very best, but on the very beginning, but this was at least my best explanation now to explain to you how we come to these conclusions in the detailed analysis. And after the next presentations, I'm looking forward to get some questions in the chat. Now we come to the next presentation of Robin Smith, and I will hand over to Robin Smith now and his presentation.
Thanks, Gerfried. Yeah, thanks for having me. I'm Robin Smith, Director at TER and an adjunct professor at the University of Technology, Sydney in Australia. Next slide, please, Gerfried. Yeah, so basically the previous presenters already talked a lot about it, but very quickly, LCA is a very powerful tool, as I'm sure everybody is aware now. It's basically a systematic evaluation of all the aspects of a vehicle's life and its associated impacts, and those impacts can vary to a great extent, and there's different ways of looking at an environmental impact, as Gerfried already discussed. But I like to split it in the energy cycle and the vehicle cycle. So the energy cycle is also referred to as the well-to-wheel, wake, wing analysis, which I will talk a bit more about specifically this presentation, which includes the fuel, electricity production and distribution, and also importantly the on-road driving and maintenance. The vehicle cycle is basically anything related to the production and the disposal of the vehicle. I think it's important in any LCA to consider four important elements to ensure that we get reliable and robust results. This is from our own experience. First of all, it needs to be country specific as much as possible. So there's a range of key factors that can vary substantially between countries and even regions, and they need to be considered wherever possible. Also, they need to be mode specific, and I will talk a bit more about that in this presentation. So when I talk about different transport modes, I'm not only looking at road transport, but also rail, air, and sea transport. And they all require different methods in terms of their impact estimation. By definition, LCA has a wide scope and has the risk of disappearing into a rabbit hole, because you can go to the nth degree in quantifying and analyzing different aspects. So that's one of the main challenges, I think, of LCA. And also on top of that, robust LCA input data can be limited and uncertain and needs to be dealt with as well. And the last point is time dynamic. It's not the same as the dynamic that Gerfried talked about. What I mean here is that things are changing very rapidly in the transport space and the renewable energy space. So things can become quite quickly outdated. So you really need a system that can quickly update the LCA results. Next slide, please. So I'm just going to quickly talk about two studies that we did, one for passenger vehicles and one for trucks. And they're all open access papers, so if you're interested in the details, they can be accessed. I just want to point out at the front that our focus is really on the greenhouse gas emissions, and as Gerfried pointed out, that is just one of the aspects that you can look at in LCA. But in the transport sector, at least, it's possibly the main driver of the changes that we're undergoing at the moment. So greenhouse gas emissions by itself are really important. Our focus is on the functional unit is grams per kilometer for passenger and freight, but also grams per ton kilometer for freight transport. So getting back to the modeling approach that we typically use. So the first step is to include all the key variables in a mathematical formulation of the model, of the LCA model. And then the second important point, referring back to the previous elements that I talked about, is to include uncertainty and variability in the inputs, specifically, explicitly, and then also reflect them in the outputs, which means that you can use the results to estimate plausible ranges, to test the robustness of the results, and to do sensitivity analysis, for example. And the schematic on the right, sorry, thanks, Griffith. Yes, the schematic on the right basically shows this process. So there's different ways of analyzing the inputs. So we prefer to use as much as possible empirical data and then apply specific statistical appropriate techniques to analyze those. Of course, there's software and tools available that can be helpful, including additional information on uncertainty. Scientific literature review is always important because there's a lot of work happening around the world from which we can learn. And if that all else fails, there's always stakeholder consultation and expert judgment. But the main result of that is a formulation of input distributions, which can have different shapes and forms, as you can see in the picture. And that is then used in a Monte Carlo simulation to propagate the uncertainty and variability through the model, resulting in a distribution itself, as you can see at the bottom. So just a few examples of key variables that we normally include in LCA models. So for example, lifetime mileage and service hours, they are linked, but they are obviously very important. If the functional unit is kilometers or ton kilometers, the emission intensities of the different types of fuels and energy is quite relevant. Vehicle specifications is, of course, quite relevant as well, and needs to be used to achieve a good classification of the transport units you're looking at. And in particular, the variability in battery, the fuel cell, and the tare mass of vehicles is quite relevant for LCAs in our experience. The durability of batteries and fuel cell systems is a critical factor, and we explicitly modeled that with a system replacement factor, and there's a lot to be said about that particular aspects of the LCA, and also very time dynamic. The payload of the vehicle, the various losses in the systems like battery charging, leakage of hydrogen, grid losses, etc., need to be accounted for. An important one is real world fuel and electricity consumption per kilometer. And of course, this real world energy use is a function of other variables like the tare mass of the vehicle, the year of assessment, etc. And that brings me to the last point, which is the internal dependencies and the feedback mechanisms that need to be explicitly modeled. And on the chart at the top, you can see an example where the normalized energy consumption is plotted against the normalized truck mass. And you can see that those are typically non-linear relationship, but not only a function of the energy consumption, but also of the driving conditions, for example, arterial driving versus freeway driving. So those things need to be accounted for. Sometimes simulation can help. So in this case, we're interested, for example, to get a insight in the distribution of the battery mass for heavy commercial vehicles in 2019, battery electric trucks. And we didn't have a lot of information for it, so instead we went back to first principles and formulated the plausible distributions for battery capacity and battery density, and then simulated that to create the input distribution for battery mass, which is then combined in the LCA model later on. One of the things we're doing as well is truncating those distributions because we don't want to have unrealistic input values. But like I mentioned before, the use of empirical data is preferred. So, for example, for diesel trucks, we actually have data on the vehicle weights, which we have then processed and statistically analyzed to create useful parametric distributions. So getting to the results now. So I won't go into all the details here, but just sort of very quick look through the results. Our results were specifically done for Australia. So basically what we found in line with studies around the world is that battery electric vehicles for passengers reduce life cycle greenhouse gas emission rates normalized in CO2 equivalents per kilometer. Specifically, the Australian electricity mix in 2018 was mainly fossil fueled still, 80%. We still found a reduction of 30 to 40%, and that's mainly due to the superior energy efficiency of the battery electric vehicle that Gurpreet already mentioned as well. But in a more renewable electricity scenario where we only assume 10% residual fossil fuels in the electricity mix, you get deep reductions of 75 to 80%. And that's not a future scenario, really. As you can see, I live in Tasmania. We already have 70 to 77% reduction because it's mainly hydropower and wind energy here. So, and it also highlights the difference between the states, which we also see in Europe and the United States, where there's similar differences in the different regions. The other interesting thing, of course, is then to look at what are the relevance. What is the relevance of the different aspects of the LCA? And we find time and time again that the operational side, so the on-road driving, is most important. So about 70% of the total life cycle emissions is accounted for by on-road driving for both fossil fuels, so petrol, diesel cars, as well as battery electric cars. And the vehicle production side, the electric vehicles are higher, as also has been observed around the world. But that's compensated for by the upstream emissions in terms of electric vehicles, which are lower than diesel and petrol cars. Next slide, please. So for trucks, this is a more recent study. We collaborated with our European colleagues here. We had many interesting discussions because it's a bit more challenging to quantify trucks. We looked at three different truck classes defined in terms of gross vehicle mass, less than 12, 12 to 25, and more than 25 tons. And I think that last category is particularly interesting, as we will see, because we use a lot of B doubles, double two-trailer trucks or more combinations in Australia, and that has impacts on the LCA results, which I will discuss soon. For 2019, we found that diesel and battery electric vehicles for the smaller categories are more or less similar, but for the large trucks, actually diesel was had a better emissions performance, and this is of course due to the high energy carbon intensity of the electricity grid in Australia at the time. This is now changing very quickly. So of course we looked at the decarbonized situation where the battery electric trucks perform the best, as you can see in the shifting distributions with the green circles. So battery electric vehicle trucks again provide deep reductions of 75 to 85%. Fuel cell vehicle trucks have a significant reduction of 50 to 70%, but I'd like to point out that the battery electric vehicles provide an additional 45 to 50% reduction as compared to the hydrogen trucks. So that's quite significant in a time where we really need to rapidly reduce greenhouse gas emissions. So just in summary here, so you can see the distributions for trucks in 2050, I think, on the right side, again, split between the different aspects of the life cycle assessment. The overall message, again, is that the energy cycle dominates the life cycle, total life cycle emissions. And of that, the operational emissions or the on-road driving dominates the life cycle emissions, varying between 50 and 85%. The vehicle cycle is not that relevant for diesel trucks, but it's more relevant for electric vehicles. dispose and recycling seems to have a minor impact in our calculations. We also compared with international studies, and we compared it with the IPCC 2022 review. And in general, our results, which you can see at the top, compare quite well with the results from the range of reported study by the IPCC. But there's two things that sort of stand out. The first thing is the low emission intensity of our heavy articulated trucks in Australia. What I mentioned before, we have two trailer or more trailer combinations for the trucks, and that really improves the emission performance of the heavy trucks when you look at diesel engines. So that is a significant difference with the international studies. The other thing that's quite different is the wide range that we've estimated for hydrogen trucks. And that is, I think, specifically because we simulated the uncertainty on many aspects of these types of trucks. We didn't hide them, we just simulated them. And as a consequence, they can produce the highest emission intensity of all the trucks even considered. And we didn't see that in the IPCC studies that were reviewed. And that might be an element of the way we explicitly model the variability and uncertainty in the LCA performance statistics. But in essence, we found that the battery electric trucks improve and converge over time in the most sort of the most strong manner, and also the most robust. They have the most narrow distribution at the end, which means that the results are most likely to happen. The fuel cell electric trucks, they improve over time, but are quite uncertain and not robust, as you can see from the plot. Next slide, please. Perfect. So what about the other transport modes? So I will very quickly touch on those. We did a very quick literature scan, and it appears at first sight that the majority of LCA studies really focus on road transport. But of course, there's other sectors that are relevant and important as well. Actually, in fact, the other transport modes, when we talk about air transport or shipping or rail, the energy cycle may dominate even more. And this is because those vehicles have very long lifetimes, relatively speaking. They typically have long operational hours and travel large distances. And the other thing is that different functional units could be of interest, for example, total emissions, which I will touch on soon. And just quickly to recap, so the LCA is the best method because you basically look at the energy cycle as well as the vehicle cycle, whereas the well-to-wheel, wing and wake only look at the energy cycle. But the good news is that typically that captures most the bulk of the life cycle emissions. So it's a good estimation if there's no better information available. Next slide, please. So we did a study last year where we did well-to-wheel wake wing analysis for intercapital transport in Australia. Again, open access. So if you're interested, please have a look. So I won't have a lot of time to go into the details, but basically the first step is to define the transport units that are of interest. So for passenger vehicles, we looked at the whole fleet mix, basically, including the different types of vehicles and the powertrain technology mixes that occur now and in the future. We looked at high-speed rail, which is not available in Australia yet, but definitely of interest. For air, we looked at the typical domestic planes, the narrow-body single-aisle aircraft like the A320 and the Boeing 737. For road, we looked at the B-double that I mentioned before. We looked at freight trains, whether they're diesel or electric. We looked at typical ships that are used in Australian waters, the bulk carriers and container ships of specific size. And again, we looked at the same planes, which are also used for freights. So we looked at a specific case study here, which is called the Inland Rail Project, and we compared the four transport modes. We looked at passenger as well as freight for 2019, 2030, and 2050, and we looked at the energy cycle emissions here. And the first thing that becomes obvious here is the when you compare different transport modes, that the distance of travel can vary significantly. So sea transport has 60% more travel distance than air transport. And of course, this is important for emissions and need to be considered in the LCA or the well-to-wheel study. One of the other things that is important is for any, like I mentioned before, the different transport modes have different models, different methods to estimate emissions, but all the methods basically uh, include vehicle mass as a key variable in the energy, fuel consumption, or emission modeling. And you can break vehicle mass down into three components: the empty mass of the vehicle, the payload, and the fuel. And as you can see in this table on the right, there could be some significant variation between the different transport modes. And in particular, for example, aircraft, the fuel mass makes up quite a large proportion of the vehicle mass, varying between 15 to 30%. And that is quite significant because during the flight, a lot of this fuel is being used. So the impact on the energy use and emissions need to be explicitly modeled because of that specific characteristics of air transport. We use different models for the different transport modes. Next slide, please. And just to point out a few things, when you start looking at other transport modes like shipping and air travel, they basically take place in moving media. So you need to start to take into account things like ocean currents, wind fields, and those sort of things. Another specific aspect for air transport is the non-CO2 climate effects like contrails, air-induced clouds, and ozone formation, which can have quite a significant additional impact on climate change. So we explicitly included those in the modeling result as well, including their uncertainty again. What we've seen happening in the past is that studies excluded them because they're highly uncertain, but in our case, we actually explicitly model uncertainty so we can include them that way. Operational conditions, of course, are modeled for all those transport modes, and things like vehicle occupancy and payloads become quite important and can be quite different transport modes as well. And next slide, please. So these are the results, the distributions for freight. And you can see that aircraft is at the bottom, is on a different scale. It's about 10 times higher than the other transport modes. This is for freight. So the emissions performance for aircraft is significantly higher than the other transport modes that we looked at. Next slide, please. Sort of an easier way to present this is as a time series. So you can see passenger transport on the left and freight transport on the right. Starting on the left, actually for both transport modes, we see that electric rail has the deep and most robust greenhouse gas emission reductions of all the transport modes. Road transport is stable, increases even a little bit for passengers because of the increased size and weight of the on-road vehicles being sold in Australia, and I think that's a similar trend all over the world at the moment. Air transport, obviously, for passengers is quite uncertain and higher as well. But when you look at freight transport, sea transport is actually also quite low, although also quite uncertain. But I think the main message here as well is the different trajectories that are being taken by the different transport modes. So electric rail is decarbonizing very quickly in line with the decarbonisation of the electricity grids, and therefore the cumulative emissions will be significantly lower than transport modes that take longer to decarbonize. I did not include the aircraft emissions on the freight transport because of the different scale, as I showed in the previous slides. Next slide. So just going to the conclusions now. The LCA is the best method, and it's versatile and very powerful, as Gerfried and previous presenters already discussed. But well-to-wheel will generally capture the bulk of the total life cycle emissions. So it's a reasonably good first estimate, I would say. But for any of those studies, it's critical to reflect country-specific data and information, to assess the uncertainty and variability in the results, and also to have a system in place that enables rapid and cost-effective updates. In our studies, we've basically seen that electrification of the on-road fleet is the most robust way to reduce greenhouse gas emissions from road transport. And we also saw that the different life cycle aspects have different contributions, and the difference is most pronounced for diesel versus electric trucks. Battery electric vehicles are expected to achieve the deepest, most reliable, and robust reductions in life cycle greenhouse gas emissions, and therefore carry the lowest policy risk of not delivering anticipated emissions performance, which is, I think, very important at this point in time. And then last point basically is the non-road transport LCAs, I think, is an emerging area, and we're quite interested to keep an eye on that and keep our work in this area as well. Thank you very much.
Thank you very much, Robin, for this interesting presentation. And now you have the possibility to ask questions in the chat. I will see the questions here. Yes, one question is if we're going to share the presentations and the recording. Yes, we will share the recording and the presentation. You will receive an email with all the details where you can get this information. I see no further question from the audience. So if you have a question, please put your question in the chat. Otherwise, I have to ask Robin a question. I once heard that the electrification of a container ship is only possible if each container is having a battery on board. Would that be somehow realistic? Does it work?
Yeah, I think well, this is of course the big question, for long haul transport with ships. It seems problematic. It will be the same as with small trucks. You start with short distance, short sea shipping, where the distances are doable with shore power. But yeah, I think it's definitely a more challenging area to decarbonize. But then again, things are happening very quickly. There's lots of developments in the battery sector, so yeah, it's a very dynamic area, Gerfried.
And we have now another question in the chat. What do you think it will bring the impact on LCA of other fuel types like ethanol, diesel, or other? So at least at biofuels.
Is that a question for me or for you?
Yeah, if you can answer it, I think it's somehow addressing biofuels. We did not consider biofuels so far, neither you, neither me. For the biofuel, it really depends on what is the raw material and which biofuel you're going to produce. And so far, we have no direct comparison in the task 46 we did so far. We excluded biofuels, at least from the very beginning, because the area of biofuel and LCA is even more complex. So we at least focused more on circularity issues and climate neutrality issues. Maybe at the next step, we can also look on biofuels, but so far we have no analysis done in the same format for biofuels. Did you work on biofuels, Robin?
Really. Yes, well, we have included it in the mix of fuels for passenger transport because we have E10 as a fuel, but I haven't like you explicitly included biofuels as a separate option now.
Yeah. Another question came up. Can you anticipate any policy changes as a result of our interesting studies? So do we change policy with our results? Maybe that's the question.
Yeah, I think in my case, I think the mode shift study in particular has generated a lot of interest. In Australia, there's quite a bit of interest in the results, and I think at least it starts the discussion. I think what I've seen a lot happening is that studies done in the US and Europe are not directly translatable or cannot be used directly in Australia. So you need to have some calibration, and I would probably think that that would be similar for other regions as well. So when we actually generate some specific numbers for Australia, that is interesting, I think, because we can sometimes find some significant differences, as I've shown. In terms of policies, yes, I think mode shift is something that is mentioned a lot, but not actioned upon yet in the policy area. But I think it all starts with good information, and then you can build the policies on that.
Maybe I can add on that this technology collaboration programs, at least from the IAA, in this group, in the executive committee, the national representatives are there, and most of them are coming from governmental organizations or ministries. And I would say when we present from not only from our task, but also from other tasks, our results in that group, at least the people from the ministry see what scientist is doing and what are key conclusions from the scientific side. We always formulate also key policy communication measures, so on. So I think on the medium to long term, I'm quite sure that also our findings are finding place in policies, because some of the policy is also done in the ministries and in governmental organizations. So I'm at least somehow optimistic that at least the real facts coming out from LCA will really help policy, and we all need a clear change towards a more sustainable transportation sector in our case. And as you mentioned, Robin, we've seen that if we go for a further electrification, that's a win-win situation anyway. Yeah? So this is really a simple but a clear shown message from our work.
Yeah, and I think in essence, the LCA tool is just very, very powerful, especially if you start to include more factors like you've shown, Gurpreet. It just gives you a very good overview of the impacts of different technologies in a holistic way, and I think that's really important. If you don't do it, you might miss things, and for policy, it's quite important to minimize those risks, that you not overlook anything. So yeah, I think this is quite useful.
I see just there came another question about the ethanol grade and the projection of the carbon intensity for these fuels in the use phase. So at least we are not the experts on ethanol, so maybe we cannot answer these questions today. But the other question was if in our assessment we also consider other environmental impacts. In the case study we did, we only analyzed the existing ones I've shown to you. My question to Robin is, you mentioned you have a strong focus on the transportation sector, as a strong focus on greenhouse gases. Do you also consider other impacts, or are they not so relevant?
Well, we've set up the system so other aspects can be included, but we haven't done that. For example, I would be quite interested in costs as well, but we haven't done that yet. Definitely interested in the future to include that.
And the last question I'm going to answer is, the question was if we also consider the need for a battery change through the truck's lifetime. That's a very relevant question. To be honest, in our case study on trucks, we did not touch that one, but we made another one on buses, which will be published quite soon. And in this study on buses, we included the battery change, but also the change of the fuel cell for the hydrogen fuel cell vehicle. And at least what I can say, this does not change the overall picture. Yeah, it's at least it's an additional input for the electric system and for the hydrogen system, but in overall the final results are still similar, that still the pure battery electric vehicle has the best environmental performance. And that leads me already to the end of our webinar by giving you a small outlook for further possibilities to interact with you. We are planning the final workshop of this task 46, which will end in year 2025. We are having a really in-person workshop where we are going to present all the main results from our work. All the partners are going to present. It's taking place in Vienna in mid of May. It's life cycle assessment of electric vehicle, steps towards circularity and climate neutrality. So if you're interested to participate there, of course, you're highly welcome. We are sending out now, we're really starting the advertisement now. And if you need further information, look on the webpage or directly contact me. Finally, I want to conclude the webinar today, maybe on a little bit visionary view on a really 100% circular and climate neutral transportation system, because we have started now also a new task concerning electric vehicles and circularity, where we apply all the aspects of circularity. These are these 10R principles. And this means in our overall system, we first have to start with the mobility demand and really see what will be the current and the future mobility demand, because then the transportation service from the technical system, and in that technical system, in an ideal case, all the materials will flow in a circle in future, because everything is repaired, everything is reused, everything is recycled. This is the ideal case. This is the visionary case. But to make this cycle turn around, of course, we have to power it with renewable energy. And this might be on long-term run, at least where we all have to go to transform our system, transportation system, to a very sustainable system. And this is at least the end of the webinar. As I mentioned before, you will receive an email with the informations to get the slides from and the recording from this webinar. If you have further questions, you can also directly send them to Robin and me. And finally, it's up to me to thank very much the audience for participating in this webinar. Thank you for your interest. Thank you for listening. I also have to thank the colleagues from Urban Foresight in the UK. You did not see them, but at least they helped to organize all the technical stuff in the background that worked so well. So it's really a big thank you to Urban Foresight and that they really organized this nice thing. And thank you very much also, Robin, for participating, because for him, he has to go to bed quite soon, because in Australia, I think it's getting dark already. So also due to the time difference, thank you very much for joining us. And if you have any further interest in our activity, please contact us. Thank you very much. Have a good day, have a good night, have a good lunch, have a good dinner. Thank you very much. And I hope we will be in touch and meet each other, at least online or in Vienna at our in-person workshop again. Thanks a lot and bye-bye.